Hello, today we are going to briefly consider what parametric functions are. And this lesson video really is not a calculus video. We are really just looking at a new region of mathematics where we have more than one variable. Actually, I shouldn't say that. I should say more than two variables. So usually we look at things in the Cartesian plane. The Cartesian plane, by the way, is named for Rene Descartes. The story is that he was ill. At least this is the story one of my math professors told me. He was ill and had to be in bed, and his brain was just thinking and thinking, as brilliant folks will do. And he noticed that the ceiling had squares on it. And he had been thinking about some different mathematics and realized that he could represent that mathematics using the square grid of the ceiling if he thought about the two components as directional. And so that is where we get the idea of the Cartesian plane with an x and a y axis, and then the collection of points then making a curve and so on. Now this understandably is very natural to us because we've done it for so long, but everything was made at some point in terms of mathematics. So we should honor Rene Descartes for his contribution there. Anyway, so usually we deal with just x and y. However, and we usually think of x as determining y. However, we could also consider a situation where we have a third variable. So parametric functions are those where there's some parameter, the third variable, and so that's where this name comes from, some parameter that is going to be determining the other two, the x and the y, in the coordinate plane. So oftentimes that parameter is t, sometimes that parameter is theta for an angle. Sometimes that parameter is just some other, don't get too hinged on the fact that it has to be t or it has to be theta. It could be any letter, really, right? I could decide I want to have p be my parameter and then have that variable be the thing that it's driving the other two. So usually that's not the case. Usually, in fact, the parameter is most often time. And then the idea is that time determines the x and that time determines the y. So my wonderful colleague, Mr. Covey, wrote this wonderful explanation down here and talked about why it matters that we might want to have a third variable. So if you're thinking about airplanes, right, air traffic controllers are those who make sure that airplanes don't crash into each other. And it would be totally fine to have a flight plan of one plane that goes somewhere and then a flight plan of a plane that goes somewhere, and both those planes maybe cross some point in three-dimensional space. It's fine that they both go through that point as long as they're not there at the same time, right? That's the issue. So the location is only part of the situation there. It would have to also consider the idea of time. And so that is what parametrics allow us to do. They allow us to consider that third possibility. So instead of just saying, what is y when x is something, you can ask, what is x when t is something, and what is y when t is that same thing? So it's really more like, instead of saying what is y when x is 2, you're going to say what is y and what is x, or excuse me, yeah, I guess I said that I just said it backwards of the print. What are x and what are y when t is, 2.7, right? At time 2.7, I want to know the location, right? All of that writing on this page, I just kind of talked around it. I would recommend just reading that. It doesn't take that long to read, and it is actually a decent explanation, I would say. I can say decent, and I can actually say good, because I think that was originally written by Mr. Covey. All right, let's take a look at a couple of examples, and we are largely going to be working these by hand here just to develop our intuition. However, a lot of times you will have calculators available to you, and you will, well, we'll talk about the calculator in a minute. Let's just do the by hand now, okay? So notice that with a parametric function, you are given two pieces, or two equations. Okay, you're given two equations. one that's x relative to the parameter and one that's y relative to the parameter. And so much like when you started graphing Cartesian equations in the first place, a nice idea is to just organize yourself in a table and say, okay, I'm going to think about different values of t. I'm going to find out what x goes with each of those values of t. I'm going to find out what y goes with each value of t. And then this graph is an x versus y graph still. You're still drawing that out. It's just that t is the thing that is driving the location, okay? So if we're looking here, let's just consider points, whole number values of t. No need to be fancy. And then for x, we need to subtract 2 from each of those because that's what the equation says. And for y, we're going to take this square root. So 1 minus the square root. So this will have some awkward values, but this will be 1. This will be 0. This would be 1 minus root 2, which is going to be negative 0.4-ish. And this will be 1 minus root 3. So that will also be negative. That's close enough for our purposes because we're just plotting a graph on very small squares, and negative 1, okay? So now when it comes time to actually draw the graph, remember that this is my ordered pair. So negative 2, 1, okay? I will do that. Negative 1, 0, 0, negative-ish, 1, negative-ish, 2, negative 1. Okay, so I can see that as t increases, these points are being generated in the manner that we are going like this. And it looks to me like we're probably going to keep going. And the way that the order in which these points are popping up is indicated by these little arrows that I've just tried to add. Maybe yellow is not the best choice. I'm not sure. Maybe blue. I'm probably just making it worse. Okay. So the pattern of the graph is going left to right. And so with a parametric function that we draw by hand, it is nice to indicate, oh, my hand is just bumping something. Eek! So it is nice to indicate something about the direction in which you're moving, okay? And so we do that with arrows, all right? Good enough. The last part of this does say eliminate the parameter. So this particular problem works very nicely if you treat it like a system of equations, right? Think about this as a system of equations. And so I know from that, I'm going to write down here at the bottom in red, that t would be x plus 2. And the second equation, if I rearrange that a little bit, I'd have, actually, I'm not going to rearrange that. I take that back. I'm going to take this and put it in for t. Into the second equation, right? So now what I just wrote down here is my rectangular equation or my Cartesian equation, right? Renee did Cartesian equation. It has x versus y, and there's no mention of t, and in fact, I just have one equation. Now, if you think about this, it makes sense with the graph because the parent function for square root looks like this. So this is a square root function that has been moved 2 to the left, reflected, moved up 1. And that's exactly what I see there in the picture. Okay, let's look at number 2. All right, we are going to, again, make a table of values. We're going to have different t values, x values, y values. Now, looking ahead, I have things that are based on trig. So let's not just use like 0, 1, 2, 3. Let's use things that we know about from our trig life, our trig enjoyment, our trig party. All right, those look pretty good to me. You obviously could use other ones from the classic unit circle values. All right, so x is going to be, well, I'm just going to speed ahead, okay? So I'm going to pause and fill in the chart maybe, if I can figure out how to do that. Maybe I can't figure out how to do that. New technology, old people, it's very, very hard. Okay, I just did that in my head. All right, so it's plug and chug math. All right, just plug things in. I picked things that were convenient for cosine, right? Cosine is nice in the 60-degree family and in the 90-degree values, right? So I just picked those. Now, these are not going to be as nice because sine at the 60-degree family is going to involve root 3 over 2. So these aren't going to be quite as, clean. You have to be comfortable with awkward numbers a little bit. Okay, so I'm not really explaining what I'm doing, but hopefully you understand. I'm just substituting in the values for t. Okay, and so this would be 3 times like 0.8 plus 1. So like 3 point something, 3 point something. I'm pretty sure. Okay, so let's see how that goes when we plot it. So remember, I'm only plotting the ordered pairs that are in purple ink there. So I've got 1, 1, 0, 3-ish, -1, 4. Notice the order in which I'm plotting these because that's going to tell us about direction. Oh, that's a little bit of a miss. -3, 1, -1, -2. 1, 1. Okay, so I think what we've got going is we started over here and we went this way. And by nature of the unit circle, I think when we get back to this point that I have in red right here, we're probably going to just keep cycling around. That looks like it's probably an ellipse. And so to verify that, we could eliminate the parameter. Now, in this particular problem, I am not going to go to inverse trig, friends. I'm not going to think of it just like a system of equations. What I'm going to do instead is understand that I know a trig identity. And that trig identity is that cosine squared plus sine squared equals 1. Okay, that's just a moment of inspiration that someone might have. And so here, if I isolate for cosine of t, I'd add the 1 and divide by 2. And that would give me an expression for cosine of t, and then this square is going to still be there. All right, here, if I isolate for sine of t, subtract the 1 over, so I have y minus 1, and then divide both sides by 3. Oh, why do I keep doing that? You guys are just, I know. You'll have to explain to me in class what it is that I am doing wrong. I am bumping something here in Notability. It must be hard having an old lady teacher. Okay, so over here, we've got y minus 1 over 3 squared equals sine 1. Okay, and hopefully you can see that that is in the format of an ellipse. Right? If you've studied conic sections, remember things about conic sections, right? This is like having the parentheses around x plus 1 squared, and then on the bottom having a 4. The next term is like having y minus 1 quantity squared over a 9, right? And so that's telling you that the center is at -1, 1, and you have one direction that goes out, based on the bottom numbers here, right? You know how far you're going out in each direction. That's actually more than we need to know for this, but I'm just pointing out that it does connect with math that you've learned before. Okay, now in your packet, we have some parametric practice problems, and there's a copy on page 18 of the answers to these questions. These are not required. However, if you're having a hard time with parametrics in general, I would encourage you to use these as practice problems rather than searching the internet. This is questions roughly of the right level. I would say that none of this is calculus yet. Have you seen a derivative? No, you haven't yet. Okay, so all this lesson was about like kind of a pre-calculus level understanding of parametrics. So keep that in mind. These are not going to be basically like, you're going to get calculus questions on a calculus assessment. But this is background that you need to know. See, these are the answers, okay? Here, we do have this page that gives you some reference material about how to use your calculator with parametrics. And one thing that I want to make sure to talk to you all about when we're in class together is changing this part to be what I call the ball and chain. So please make sure that I talk to you all about that live in class, okay? Otherwise, this page is everything that I would want to tell you about parametrics. So please read that and use those screenshots along with your own calculator to help yourself get your bearings, because a lot of the times, if you needed a graph of a parametric, you would use your calculator. To be honest, there are a lot of parametric questions you can answer without ever seeing what the parametric looks like. And that's totally fine. That's the power of calculus, that you can know rates of change and how things are moving, even if you don't have a picture. Okay? So that's all I wanted to talk to you about. Thank you so much for listening. Thanks for dealing with my technology goofs. Okay? Thank you so much. Bye-bye.